You know, there's a number that keeps physicists awake at night, staring at the ceiling, wondering about the fundamental nature of reality. It's a very, very big number, and it's worth taking a moment to really appreciate just how staggeringly large it is. If you look at the universe, really look at it carefully, and you try to count all the stuff that makes up the matter we can see, all the stars scattered across billions of galaxies, all the nebulas glowing in deep space, all the dirt in your backyard, the atoms in the chair you're sitting on, the skin covering your hand, every single bit of ordinary matter. And if you count every single electron in all of that matter throughout the entire observable universe, you end up with a number somewhere around 10 to the power of 80. That's a 1 followed by 80 zeros. It's a number so absolutely colossal, so mind-bendingly enormous, that our brains cannot even begin to properly imagine it. We can write it down, we can manipulate it mathematically, but we can't truly visualize it. It's just an abstraction, a blur of incomprehensible magnitude. But what if I told you something that sounds completely insane? What if I told you that we've been counting wrong this entire time? What if the real number isn't 10 to the 80th power at all? What if I told you that the total number of electrons in the entire universe, from the Big Bang until the ultimate end of time, from the beginning to the conclusion of everything, is actually just 1? Yes, 1. Just one single electron doing all the work, dancing everywhere at once, weaving the entire fabric of reality by itself, alone. I know how this sounds. It sounds crazy. It sounds like something a mystic would say after spending too many hours staring at a blank wall in deep meditation. It sounds like the kind of nonsense that has no place in serious scientific discussion. But here's the thing, this isn't mysticism. This isn't New Age philosophy. This isn't some vague spiritual metaphor. This is physics, actual, rigorous, mathematical physics. And it's an idea that leads us directly to one of the most profound, beautiful, and absolutely absurd secrets about how time and matter really work at the deepest level. If you stick with me through this exploration, we're going to take this bizarre idea apart, piece by piece, examine it from every angle, and see if we can put the universe back together in a way that actually makes sense. Because nature is strange, stranger than most people imagine. But she is never, ever boring. The problem with billiard ball physics. You see, the fundamental problem with the way most of us are taught science in school is that we're taught to look at the world as a collection of separate things, like little billiard balls bouncing around on a table. We develop this mental picture of an electron as a tiny marble carrying an electric charge, whizzing around an atomic nucleus like a miniature planet orbiting a sun. And that picture is perfectly fine if your goal is simply to pass a chemistry test in high school. It works well enough for everyday purposes, but if you actually want to understand how the world really works at its foundations, if you want to glimpse the true nature of physical reality, that picture is not just incomplete. It's worse than wrong. It's boring. It's misleading. It actively prevents you from seeing what's actually going on. Because if you really look at these particles, if you study them carefully with precision instruments, you notice something very suspicious, something that should deeply bother you, something that demands explanation. Take two marbles, ordinary glass marbles made in a factory. From a distance, they look identical, same size, same color, same shape. But if you examine them really closely with a microscope, you'll find differences. One has a tiny scratch here, the other has a small bump there. One is microscopically heavier because it has slightly more glass. One is lighter. They have different histories, different imperfections. They are distinguishable. You can tell them apart if you look carefully enough. Now compare this to electrons. Take an electron from an atom in an apple sitting in your refrigerator. Take another electron from an atom in a star at the edge of the observable galaxy, billions of light years away. Bring them together somehow and measure their properties with the most precise instruments we can build. What do you find? They have exactly the same mass, exactly the same electric charge, exactly the same spin, exactly the same magnetic moment. There is absolutely no way, no measurement you could possibly perform, no test you could possibly devise that would allow you to tell them apart. Not approximately the same, exactly the same. They're not just similar, like twins who share DNA, but have different fingerprints. They are identical in a way that nothing in our everyday macroscopic world is ever identical. Perfect copies down to every measurable property. Why? Why should the universe be so monotonous, so repetitive? Why isn't there a slightly heavier electron and a slightly lighter one? Why isn't there one with a bit more charge and one with a bit less? Why isn't there a blue electron and a red electron, an old electron and a young electron? Why is every single electron in the entire universe a perfect copy of every other electron? It's almost as if they were all stamped from the same mold, produced by the same cosmic factory using the same exact specifications. Or perhaps, and this is where things get really interesting, perhaps they're not copies at all. A phone call that changed everything. Before we get to the full answer, which involves time travel and antimatter, yes, really, I'm completely serious, I want to tell you about a conversation that happened many decades ago, a conversation that planted the seed of this extraordinary idea. I was a graduate student at Princeton University. I was young, enthusiastic, probably a bit too confident, thinking I knew quite a bit about physics. And then one day I received a phone call from my professor, John Archibald Wheeler. Now, Wheeler was an intellectual giant, one of those rare individuals who had a gift for looking at a well-established problem and turning it completely upside down, seeing it from an angle nobody else had considered. He had this remarkable ability to cut through mathematical complexity and find the geometric heart of a physical idea. He calls me up, and I can still remember the excitement in his voice when he said, "Feynman, I know why all electrons have the same charge and the same mass." And naturally I asked, why? What's the explanation? He said something that initially made me think he was joking, because they are all the same electron. I paused, waiting for the punchline, but there was no punchline. He wasn't joking at all. And as he started to explain the idea to me, as he began to unpack the logic, I realized he had found a way to visualize the history of the universe, a geometric picture of space-time that completely shatters our normal intuition about how time works. Rethinking time itself. To understand what Wheeler was proposing, we have to stop thinking about time the way we usually do in everyday life. We typically think of time like a river, flowing inexorably from the past into the future, carrying us along with its current. We think now is special, a unique moment that divides what has happened from what will happen. But in physics, especially when you start drawing space-time diagrams the way Einstein taught us to think about relativity, time is just another direction in a geometric space. It's similar to the spatial dimensions, just with some different mathematical properties. It's not fundamentally different from space. Let me show you what I mean. Imagine you have a piece of paper in front of you. Draw a horizontal line across the middle. That horizontal direction represents space, let's say left and right along one dimension. Now draw a vertical line. That vertical direction represents time, with up being the future and down being the past. Now imagine an electron sitting perfectly still in space. It's not moving left or right, but it is moving in time. It's getting older. Every second that passes, it moves forward in time. So on our piece of paper, its path through space-time is a straight vertical line going upward. We call this path a world line. It's the particle's history, its trajectory through space-time. If the electron starts moving to the right, its world line slants to the right as it goes up. If it moves to the left, the line slants to the left. Simple enough, right? A world line is just a complete record of where a particle has been in space, and when it was there, a map of its entire history drawn on a space-time diagram. But then Wheeler said something profound. He asked, what if this line doesn't just go up? What if it loops back? The tangled string. Imagine you have a very, very long piece of string, longer than you can possibly visualize. This string represents the complete history of a single electron, its world line through all of space-time. Now, instead of stretching this string straight up from the distant past to the far future in a simple, orderly way, imagine I take this string and I crumple it up. I make a giant tangled knot with it. I weave it back and forth through time. I make loops and curves and zigzags. The string itself remains continuous. It never breaks. It never ends. It's just one long, unbroken path, but it's folded and twisted in an incredibly complicated way. Now here's the magic trick, the conceptual leap that makes everything else make sense. This is where you really have to engage your imagination. Imagine that now, the present moment, is a horizontal slice through this tangled mess of string, like we're slicing through a loaf of bread or cutting through a great tapestry with a knife. If I pass a horizontal slice through that tangled ball of string, through that knot of world lines, what do I see? I don't see one continuous string. From the perspective of that slice, I see lots of little dots, individual points. I see a dot everywhere the string cuts through my slice, everywhere it intersects the present moment. Some of those parts of the string, some of those dots are oriented going upward toward the future. In the context of our space-time diagram, those are moving forward in time. Those are the electrons we observe. But because the string is looped back on itself, because it's tangled and folded, some of those parts of the string must be oriented going downward toward the past. They're the same string, the same continuous path, but they're moving in the opposite temporal direction. Now here's the crucial question, the question that makes this whole idea work. What does a particle look like if it's moving backwards in time? How would we observe such a thing? This is where we have to talk about something that sounds like pure science fiction, but is actually well-established physics, antimatter. The backwards arrow of time. You see, when physicists first worked out the mathematical equations that govern how electricity and magnetism work, the famous Maxwell equations and later the equations of quantum electrodynamics, they discovered something surprising and beautiful. These equations are remarkably symmetrical. They don't really care which direction the clock is running. If you take a movie of an electron moving through space and interacting with electromagnetic fields, and you run that movie backwards, reversing the direction of time, the physics still makes perfect sense. The equations still work. Nothing is violated. But there's a subtle catch, a fascinating twist. If you reverse the direction of time in the equations, if you mathematically flip the arrow of time, the result looks exactly the same as if you had instead reversed the electric charge of the particle while keeping time moving forward. Let me say that again because it's crucial. An electron moving backward in time doesn't look like an electron moving backward. Instead, it looks exactly like a particle with the same mass as an electron, but with a positive electric charge instead of a negative one, moving forward in time in the normal way. And we have a name for that particle. We've observed it in experiments. We call it a positron. It's the antimatter counterpart of the electron, identical in every way except for the opposite charge. So when Wheeler told me they're all the same electron, here's precisely what he meant. Here's the geometric picture he was proposing. The universe is this giant four-dimensional space-time block, extending from the Big Bang to whatever ultimate fate awaits us. Inside this block, there is one tremendously long, incredibly tangled world line. It zigzags through space-time. It goes forward in time for a while, and during that portion, we observe it as an electron. Then it reaches some point, turns around, and goes backward in time, and during that portion, we observe it as a positron. Then it turns around again and goes forward, appearing as another electron. Then it loops back again, over and over, back and forth, zigzagging through the centuries and millennia, weaving and knotting, stitching together the fabric of the cosmos. If you take a slice through this impossibly complex knot at any particular moment, say the year 2024, you intersect the same continuous line billions and billions and billions of times. Roughly half of those intersections show the line going upward in time, and roughly half show it going downward. But to us, trapped in the present moment, limited to observing our particular slice through space-time, we don't see the connections between these intersections. We don't see the loops where the electron turns around. We just see billions of separate electrons scattered throughout space and billions of separate positrons. And we think they're all different particles because we can't perceive the temporal folds, the loops, where the direction reverses. It's like looking at a winding mountain road from an airplane at night. You see headlights here, tail lights there, more headlights over there. You might think you're seeing many different roads, dozens of separate highways. But if you could see the whole landscape at once, if you had the complete picture, you'd realize it's just one continuous highway winding through the mountains, looping back and forth. The problem of asymmetry. When Wheeler first put this idea in my head, explained this geometric picture of a single electron threading through all of space-time, I immediately saw what I thought was a fatal flaw. I was skeptical, as any good physicist should be. I said, "But Professor Wheeler, there's a serious problem. There aren't as many positrons as electrons in the universe. If this theory were literally true, if it really is just one string going back and forth through time, then for every segment of the line going upward representing an electron, there has to be a segment coming back down representing a positron. The numbers should be exactly equal." But look around at the actual universe we observe. The cosmos is made overwhelmingly of matter, not antimatter. Electrons are absolutely everywhere. They're in every atom of every object we can see. Positrons, on the other hand, are extremely rare. We only find them in high-energy particle physics experiments or in cosmic rays or produced by certain types of radioactive decay. Where are all the missing positrons? If your theory is right, they should be just as common as electrons. Wheeler, being the creative genius that he was, had an answer ready. He suggested that maybe the positrons are somehow hidden inside protons, or perhaps inside neutrons. Maybe they're there, but we can't easily detect them in that form. Now, I have to be honest with you, that particular part of his idea, that specific proposal about where the positrons might be hiding, didn't turn out to be correct. We know now from decades of subsequent research that protons and neutrons are not simple particles. They're complex composite objects made of quarks bound together by the strong nuclear force. They're not just hidden positrons. The matter-antimatter symmetry isn't perfect in the simple way Wheeler guessed in that initial conversation. But here's what's absolutely crucial. Here's what survived and became foundational to modern physics. The core idea, the fundamental insight that a positron is mathematically equivalent to an electron moving backward in time, that profound realization stuck. It became a cornerstone of how we understand and calculate quantum electrodynamics. The mathematics of antimatter. When we draw Feynman diagrams today, those little pictures I developed to help calculate how light and matter interact, how particles scatter and exchange energy, we actually draw positrons as arrows pointing backward in time. This isn't just a convenient bookkeeping trick or an arbitrary choice of notation. It's a fundamental insight into the geometric structure of reality, into how space-time and particles are woven together. Think carefully about what happens when an electron meets a positron. This is something we can observe in particle physics experiments. They annihilate each other. They vanish, and their mass energy is released in the form of photons, particles of light. The matter seems to disappear, converted entirely into pure energy. But look at this process from the perspective of the one-electron theory, from the viewpoint of Wheeler's tangled string. The electron is moving forward in time. The positron is the same electron, the same segment of the string, moving backward in time. When they meet, when they annihilate, it's actually just the point where the particle decided to make a U-turn in time. It reached a certain point in space-time and turned around to go back. So annihilation isn't the destruction of matter in any fundamental sense. It's just the particle turning a corner in the temporal dimension, changing its direction from futureward to pastward. Similarly, pair creation, the spontaneous appearance of an electron and positron seemingly out of nowhere when a high-energy photon passes near an atomic nucleus, that's just the particle turning around again, redirecting from pastward back to futureward. It's a fundamentally geometric view of the universe. It treats time as similar to space. It treats history as a map that already exists, complete and whole, rather than as something being created moment by moment. The deep implications. Now I want you to pause for a second and really let that sink in, let it percolate through your imagination. Really think about what this means. This idea suggests that the electron in the tip of your finger right now, at this very moment, could be the exact same electron that was once part of a neuron in Albert Einstein's brain. It could be the same electron that powered the first lightning bolt on primordial Earth billions of years ago. It could be the same electron that is currently burning in the heart of a star a billion light years away in some distant galaxy. The path of this electron through space-time is impossibly complex. Maybe it takes a journey where it lives as part of the chemistry of a dinosaur for millions of years. Then perhaps it turns around, travels back through time all the way to near the Big Bang, turns around again, and becomes part of the screen of a smartphone in the 21st century. It means that the distinction between this electron and that electron, the separation we perceive between different electrons, is an illusion created by our limited perspective, by our inability to see the temporal dimension in its fullness. We are slicing the sausage of space-time and thinking every individual slice is a completely separate object, but it's all one continuous thing. It's all one piece of meat, one thread, one string weaving an impossibly intricate pattern. Further, why this matters. So why should you care about a theory that sounds this absurd, this divorced from everyday experience? Why does this matter beyond being an interesting intellectual curiosity? Because it challenges one of the most stubborn illusions we carry around with us every day, an illusion so deep we rarely even notice it, the illusion of separation. We look at the world and we see distinct, separate objects. We see me and you. We see here and there. We see now and then. We build our entire understanding of reality, our whole lives, around these separations. We think that objects are distinct, independent actors on a stage, each with its own separate existence. But quantum mechanics, and specifically this geometric view of quantum electrodynamics that grew out of Wheeler's insight, tells us something radically different. At the deepest level, we can probe at the foundation of physical reality. Identity becomes blurry. Separateness dissolves. The fact that you cannot distinguish one electron from another, the fact that they are perfectly identical, is a hint from nature. It's the universe whispering to us that the manyness of the world, the apparent multiplicity, might be a surface phenomenon, something that emerges from a limited viewpoint. Underneath, there might be a unity that is harder to see, but much more profound and fundamental. The honest assessment. Now, I have to be completely honest with you, because that's the only way to do science properly. You have to be rigorously honest, even when it's inconvenient. Is this theory, the literal idea that there is only one physical electron threading through all of space-time, accepted as absolute established truth in physics today? No, it isn't. There are significant problems with it that prevent it from being a complete description of reality. As I mentioned earlier, the asymmetry between matter and antimatter is a major issue. The observable universe contains far more electrons than positrons, and we don't have a satisfying explanation for this imbalance within the simple one-electron framework. Furthermore, with the discovery of many more types of particles beyond just electrons and positrons, quarks and neutrinos and muons, and a whole zoo of other particles, the picture becomes vastly more complicated. We don't literally believe today that there's only one fundamental string threading through everything. However, and this is crucial, the mathematical tool that came out of Wheeler's insight. The idea that antimatter is mathematically equivalent to matter moving backward in time is absolutely correct and absolutely essential to modern physics. It's not optional. It's not approximate. It's the only way we can make the equations work properly. It's the only framework that allows us to calculate things like the magnetic moment of the electron to 12 decimal places and get an answer that matches experimental measurements exactly. Without this insight, quantum electrodynamics simply doesn't work. So even if the one electron story is not literally true, even if it's a simplification or a myth in some sense, it's a myth that points directly toward profound truth. It's a scaffold that helped us build the cathedral of modern physics. And the cathedral stands even if we later remove some of the scaffolding.